Okay, some more problems from the 9.4. This is number 14. And I wish I had a little more time to write these out again and show all the steps, but doing a lot of videos this year, so this is taking a little bit of time. All right, so let's take a look at this. So this is what we want to check, this function. We're going to use a ratio test. It's not a geometric series, so we use a ratio test. Okay, so again, I'm going to add 1 to every n, so use the absolute value because we'll check for absolute convergence. And remember, absolute convergence implies regular convergence. So I'll take the absolute value of this. So the absolute value, and then we're going to raise this, and this is going to be the n plus 1. So every time I see an n, I put n plus 1. So this is 2, n plus 1, and I keep that in parentheses, plus 1, so don't forget that, all over n plus 1 factorial, times the reciprocal of this, which is n factorial, all over x to the 2n plus 1. All right, so we've got all this. Now, if I multiply this out, this is 2 times n is 2n, and then 2 times 1 is 2, plus 1 is 3. Okay, so that's the top over here. If I simplify that out, I've got over n plus 1 factorial. Now I've got n factorial over here. So here's a little trick. N plus 1 factorial means n plus 1 times n minus 1. So this is basically n plus 1 times n factorial. So we can write this out like this, because that's n plus 1, then all those other terms. Factors, I should say, n minus 1, n minus 2, etc. And I did that because these n factorials can cancel, so I can get that factorial out of there. Okay, and that's all I did. This stayed the same. So what happens with these factorials? They become 1. Now look over here. If I cancel these, or if I divide it out, if I have 2n plus 3 minus 2n plus 1, that's just going to be 2n plus 3 minus 2n minus 1. The 2n's cancel. 3 minus 1 is 2. So this is what I have left. Okay, my n factorials cancel, so I've got n plus 1 on the bottom. So this is all I have left on the top. So I can move this in front, so I can take the limit, because the x is involved in the limit. And the limit as n approaches infinity of n over n plus 1, this becomes very large. Over 1, it's 0. So 0 times x squared is 0. All right. So that means that L equals 0, because this is L. Well, by the ratio test, the series converges whenever L is less than 1, correct? Well, 0 is always less than 1, regardless of the value of x. 0 is always less than 1. So therefore, L is always less than 1. Therefore, the series converges all the time, or for all x. Therefore, the radius of convergence is infinity. If I got L to be 1/2 or L to be 1/4, that'd be the same thing. If L is less than 1, always less than 1, your radius of convergence is all values. Okay. All right, number 15. There we go. Okay. And another ratio test. Okay, n times x plus 3 to the n over 5 to the n. Okay, so we're going to check for absolute convergence to make sure that all of our terms are positive. So we'll take the limit of a sub n plus 1 over a sub n. So every time I see an n, I put n plus 1. So I got n plus 1, x to the 3 to the n plus 1 over 5 to the n plus 1. This is a 5. See that? And times the reciprocal of this, so I put the 5 to the n on top, and n x plus 3 to the n on the bottom. And then I broke this up. This is positive, so I don't need an absolute value. This may or may not be. X could be negative. I'm not too sure, so I need an absolute value here. And this is x plus 3. Now what I did was I broke this up. So this is n plus 1. This is x plus 3 to the n times x plus 3 to the first power. Is that all right? Okay, because this is the first power. If you multiply these, you just add the exponent, so I just broke it up. And this is the same thing with the 5. This is 5 to the n times 5. So I actually showed these steps. I think I skipped them in a previous problem. So I actually showed the steps here. So I'll break these up. And the reason why I break these up, because if I look over here, 5 to the n is going to be positive. This is positive. This I still have the absolute value. But look at all the canceling I've got. The 5 to the n's cancel. All right? The x plus 3's to the n's cancel. Okay, so I end up with n, that canceled, x plus 3, 5n canceled over n and 5. So this is what I end up with. Now if I take the limit as n approaches infinity of this, that's just going to be what? 1. Lots of ways to do it, but it's going to be 1. I mean, it's going to end up being infinity over infinity, or it's going to be the ratio of the highest degree terms. That's both 1, so that's 1 over 1 is 1. Either way, it's 1. Okay? So I just have this limit becomes 1, so it's just this. So this converges. The series converges, and this is L. Remember, this is L. Let's probably write that down. This is L. And that converges when L is less than 1. So when this is less than 1, this converges. So again, it's almost in the form x minus a. A would be negative 3 in this case. Except what we want is we want to get rid of the 5. So we multiply both sides by 5. And we have the absolute value of x plus 3 is less than 5. So there my radius of convergence is 5. Okay. And then number 16. And you go through these, make sure you check your steps because, you know, you'll make some little mistakes with the factorials and breaking these exponents up. And after you do it for a while, then you start to get the hang of it. But, you know, you don't be surprised if you make a lot of little mistakes. Just get used to dealing with this because this is the kind of arithmetic you need to do for these ratio tests. All right, so this was my series. I'm going to use the ratio test again. I'm using this limit, and that's going to be equal to L. I should say that limit equals L. And once we have that, if L is less than 1, that's what we want. If we can make that limit less than 1, then we can find our radius of convergence. So this is going to be n plus 1, x to the n plus 1, 4 to the n plus 1, and this is going to be, now careful on this one, this is going to be n plus 1 squared plus 1. See, every time you see an n, you put an n plus 1. And this is just the reciprocal of this, so I've got 4 n squared plus 1 all over n x to the n. So now we break this up like we did before. This is, it stays n plus 1. This is x to the n times x, and this is absolute values because we're dealing with that. This is 4 to the n plus 4, 4 to the n plus 4, and then I multiply this out. So I got n squared plus 2n plus 1 is n squared plus 2n plus 2 times this, which was pretty much in its native form, except I just put the absolute values where I really needed them, and that was on the x terms. Okay, so we got a lot of canceling to do. So not much of the n's cancel, do they? So I got n plus 1, n squared, those didn't cancel, and I've got n times n squared 2n plus 2. Okay, but the 4 to the n's cancel, and the x to the n's cancel, so I end up with just the absolute value of x on the top and 4 on the bottom. So now we've got to take the limit of this whole thing here. Now if I multiply all my terms out, n times n squared is n cubed, n times n squared is n cubed, so my highest degree terms will be n cubed over n cubed, and the ratio of their coefficients is 1. So that's all this is, the limit of this is going to be 1. So this is what I've got, multiply both sides by 4, and this is, well, this is actually L. Right here, that's L. That's the limit, okay? And that converges when L is less than 1. So when this is less than 1, my series converges. And I can, that's basically it. And I multiply both sides by 4 because that's my radius of convergence, because I don't want the 4 in the denominator. I don't want a fraction. So my radius is 4. Okay? So take a look at those. Watch your arithmetic. Hope that helps.